Welcome to our flipped classroom presentation. This is Chapter 13, Section A on solving problems with vector operations. We've been looking at various vector operations in 2 dimensions and 3 dimensions. What we want to look at today is just how to interpret a problem where there are multiple vectors at play, how to draw a picture, how to find magnitudes and directions, and then also what those mean. So we look at the problem here. It says in still water, Jacques can swim at 1.5 meters per second. Jacques is at point A on the edge of a canal and considers point B directly opposite. A current is flowing from the left at a constant speed of 0.5 meters per second. So here you see the situation. And Jacques is here at point A, and you have the current flowing from left to right. So it says, if Jacques dives in straight towards B and swims without allowing for the current, what will his actual speed and direction be? All right, so we need to consider the 2 vectors at play. First of all, we have Jacques' swimming vector going from A towards B. He's swimming directly at it, and it says that he can swim at 1.5 meters per second. Okay, so I'm going to call this vector S for swimming, okay. And this value right here, 1.5 meters per second, is the magnitude of vector S. Okay. Now, also at play is our current, and you can see it over here. I'm going to translate that over to here. There's our current. I'll call that vector C for current, and that 0.5 is the magnitude of the current, so that's 0.5 meters per second. So to answer our question, what will his actual speed and direction be, we need to consider the resultant vector. Now the result is going to be what actually happens. Okay, and here we have a simple vector addition. We have his swimming vector plus the current. Alright, so we need to determine how to find his actual speed and what his direction is. Now you'll notice the vectors that we're talking about here, this swimming vector and the current vector, we have both a speed and a direction. That's velocity. Okay, and the magnitude of a velocity vector is speed. So both of these are speeds. Okay, we want the magnitude of S plus C. Okay, so to find his actual speed, this is what we want to find. Alright, so how would we go about doing that? Well, you'll notice because our current is flowing left to right and he's trying to swim straight across, this forms a right triangle. And we can consider the Pythagorean theorem if we look at the magnitudes of those sides. So this magnitude squared is going to equal 1.5 squared, our swimming vector squared, plus 0.5 squared. Okay, so 1.5 squared is 2.25. 0.5 squared is 0.25. We add those together. Scroll down here. And we get 2.5. And of course we need to square root that. Okay, because that is the magnitude squared. So the magnitude we're looking for, S, the magnitude of S plus C, is the square root of 2.5. Okay. So, you can figure that out with a calculator. Square root of 2.5 2.5 square rooted and we get 1.58. We'll round to the hundredth. 1.58 meters per second. Okay. Now to find the direction, we need to determine what our direction is going to be relative to. I'll make it relative to going due north. So we're going to find this angle right in here. Okay. And again, we can use the right triangle, and we'll use some trig this time. In relation to this angle that we're trying to find, we know the magnitude of the opposite leg, the current vector, and we know the magnitude of his swimming vector, which is the adjacent leg. So that means I'll call this angle theta down here. So tangent of theta equals the magnitude of the current vector, which was 0.5, divided by the magnitude of the swimming vector. This is again opposite over adjacent. So now we need to take the inverse tangent, and we'll do it in degrees. So I'll make sure I'm in degrees. I am. And I need to do the inverse tangent of 0.5 over 1.5 is 1/3, so I'll just punch it in that way. Close my parentheses, and I get theta equal to, that was 18.4 degrees. Okay. 18.4 degrees. And that's an angle going clockwise from due north. That's commonly known as a heading. That's a common way of measuring angles in given directions. So his actual speed, 1.58 meters per second. His direction, 18.4 degrees from due north. Okay. The second part of this problem, Jacques notices that that's going to happen. That's going to get him off course. He wants to swim directly across the canal to point B. So he wants to end up at point B. So he realizes he needs to aim upstream somehow. Okay. He wants that to be his swimming vector. And the current then will correct his path and push him that way. Okay. So they're asking, what angle should Jacques aim to swim? So we're trying to find, in this case, this is going to be the resultant vector, the S, plus C. Okay, and again, this is our vector C for the current. So that's going to be the result. What we want is, what should this angle here be? Okay, and I'll switch colors again. So I'll call that theta this time. Now we'll use a similar process using trig, except this time the current is opposite and the magnitude of our swimming vector is the hypotenuse. So in this case, to find the angle, we're going to use the sine of theta, and that's going to equal magnitude of the current, 0.5, over the magnitude of his swimming vector, 1.5. Again, I need to use an inverse trig function, so this time inverse sine of 1/3, which is 0.5 over 1.5. and I get 19.47, or we'll round to the nearest tenth of a degree. Theta is 19.5 degrees. Now notice that's 19.5 degrees to the left, in a direction to the left of straight across at B. Okay, so we could write that in to the, and you can even use the directions, this would be to the west of north. Okay? So that's the direction we'd need to take. In all of these vector problems, you're going to end up using some sort of trig, or in most of them you'll use some sort of trig, possibly the Pythagorean theorem, things like that. And actually, speaking of the Pythagorean theorem, if we want the actual speed, we can use the Pythagorean theorem. It's just in this case, the actual speed is going to be one of the legs of our right triangle. So, notice our swimming vector is the hypotenuse, so that's going to be 1.5 squared equals 0.5 squared plus the magnitude of S plus C squared. Again, this is 2.25. This is 0.25 plus the magnitude of S plus C squared. I subtract 0.25 from both sides, and then I'm going to have to square root. So I subtract and I get 2, which means that's going to be the square root of 2 for the magnitude of S plus C. And if you know your square roots, or if you have a calculator, that's going to be 1.414, or we'll just do 1.41 meters per second. Okay, so he's swimming partly upstream at an angle kind of upstream. The current is pushing him back in the right direction, and he's going to end up going in that right direction at a speed of 1.41 meters per second. Okay, so for all of these, you need to make sure you have a good picture. In this case, it was kind of given to you. You had to construct the triangles, and then figure out what vectors you're using, and in relation to those vectors, what are you actually trying to find? Here we're finding an angle. Okay, over here we're finding a magnitude. Okay, if you think back to the problem we had at the very beginning of this unit, we had an airplane that was flying due east, and we had a wind affecting it. In order to figure out what that plane is actually going to do, we have here vector addition. Okay. Now both parts of the example that we just finished used right triangle trig. Here's an example where this was going due east, the wind was blowing exactly at northeast, which means it's at a 45 degree from due north. So our angle was 135 degrees. Okay, and if we then want to figure out, hey, what's this result? If we can find if we know the magnitude of the plane, the magnitude of the wind, which we were given the plane speed and the wind speed, in this case, to find out what the plane is actually doing, that speed, we would use the law of cosines, or the cosine rule. Okay, and you can run through the trig there on your own. But it's not always going to be right triangle trig. We will have situations like this, but that's basically how you would do problems involving vectors. Draw yourself a picture, And